Hello again. Today we will be talking about the link budget, including noise and propagation effects. As we recently studied, SNR is a very important parameter in the reception of signals. The SNR at the demodulator output depends on a number of factors. Of course, the type of modulation, as we studied. The signal power at the output, the noise power spectral density at the output. Okay, the signal power at the output is determined by the signal power at the input of the demodulator. The noise power spectral density at the output is determined by the noise power at the input and all the other noise sources in the system. Now, for propagation, free space in the free space, or for propagation in general in the terrestrial environment, we estimate the propagation loss using something called the Friis transmission formula. The Friis formula starts from free space loss, where the physics is sort of simpler. Suppose the transmitted power that we radiate, our transmitter radiates, is PT, P sub T. If you consider spherical propagation equal in all directions in the far field of the antenna, the received power density at a distance d will be equal to, through a spherical argument, if you go the distance d from the transmitting source, consider the surface area of the sphere, okay, at that distance. The power density, power per square meter, if you will, power per area, is going to be PT divided by 4 pi d squared. Simple free space propagation. Of course, transmitting in an omnidirectional manner like this may not be ideal to maximize the SNR at the receiver. So many communication systems contain directional antennas. So if an antenna has directivity in a particular direction such that it creates a beam, like as in this picture, it creates a beam in a particular direction, okay, we are going to see a gain, an antenna gain. This is called the transmit antenna gain. Depends on the frequency, on the construction of the antenna, on the antenna geometry, and on many other factors. Now, a receiving antenna in the direction of the radiated power gathers a portion of the power that is proportional to its area, of course. Okay, but the effective antenna area also has to do with other factors related to the design of the antenna. We summarize those factors in value called G sub R, the receive antenna gain. The effective area of the receive antenna is directly proportional to the wavelength squared divided by 4 pi. So the effective antenna area is antenna gain multiplied by lambda squared over 4 pi. So the larger the wavelength, the larger the effective antenna area, because receive antennas are constructed with the wavelength that we are receiving in mind. Okay, now if you factor this in the Friis transmission formula, okay, the received power is given by the transmit power multiplied by the free space loss, essentially lambda lambda over 4 pi d squared times GTGR. Of course, this lambda over 4 pi d squared is coming from both this term and this term. So this is PT over 4 pi d squared. And in the second one, we have lambda squared divided by 4 pi. So if you put it all together, lambda squared over 4 pi squared d squared. Okay, it is summarized here. And we are going to refer to this term as the free space path gain. Of course, we expect it to be less than 1. We really expect it to be a loss. But since it's a multiplicative factor, together with these other multiplicative factors, we're going to name it free space path gain. Okay. And the other two factors are the transmit and receive antenna gains. Okay. Are there any questions so far? Okay. So far in the course, we didn't consider propagation effect at all. And this is just free space loss and antenna gain, okay, are the maybe the most fundamental and essential things to consider in the link budget. Of course, in more advanced considerations, there are other losses, like atmospheric losses due to the presence of oxygen molecules, water vapor, right? And these effects depend on the frequency that we use. There are shadowing effects, such as those caused by absorption by buildings and other major structures, hills, trees. There are multipath fading effects that are caused by the superposition of delayed copies of the electromagnetic wave as it propagates in the environment. So all of these things change the power fall-off with distance from being quadratic to faster. For example, in an indoor environment, the power fall-off with distance usually goes like distance to the 4th power. Often in real life, power fall-off varies somewhere between quadratic to the 4th power. Okay, but we are not going to really worry about these things in this course. Okay, there are other courses in our department that deal with such issues: propagation, radio propagation, radio communication in general, or wireless communication. Those courses are EE 634. I'm sorry, 637 and EE 728. All right. So anyway, if you ever get interested in wireless communications, there are other courses, as I said, and other resources to study it. So let's go back to our link budget. Okay. Usually, the formula for a link budget is written in terms of decibels. Okay, because you know, taking logarithms helps us convert multiplication into a simple addition, and simple addition is always an easier thing to do, especially if you're dealing with, you know, multiplication of very large numbers. If you go to a log domain, it becomes easier to handle. Okay, so received power in dB is 10 times log to the base 10 of the received power in your power unit. It could be watts, milliwatts. Usually we use watts. Okay. Now, think of this formula that consists of PR being equal to PT times GT times GR times free space gain. Now, if you take the logarithm of this whole thing, you would get, and you multiply it by 10, right? You would get 10 log PR equals 10 log PT plus 10 log GT plus 10 log GR plus 20 log lambda over 4 pi d, right? So basically, the equivalent representation of this formula is PT in dB, GT in dB, GR plus GS. Now, we define LS, the free space path loss, as 1 over the free space path gain. Often, the free space path loss itself is, of course, larger than 1. 1 over GS is less than 1. Therefore, this is going to be a negative dB term, right? If you want to see that you're subtracting a positive quantity, you can think about the free space path loss. So you understand that we call it a gain, a free space path gain, but it's negative. All right. Now, okay, in case we wanted to incorporate other components, we could always factor them in as further losses. Okay, so if you are given such information, you can always incorporate such information in your overall link budget. Okay, let's try to do an example. Are there any questions so far? So in the question, we're given a GSM base station, third generation cellular base station with 5 watts of transmit power. Okay, so PT equals 5 watts. All right. So I'm going to define to you something called a dBm. Some of you may have heard about it. Okay, so 5 watt in dB, so dBm is 10 log power divided by 1 milliwatt. Okay, this would be power in dBm. Okay, what is the convenience of using dBm? You can add dBs and dBms. Okay, and the result is going to be dBm. So that is very convenient. You can convince yourself that you can add dB to dBm and the result is dBm, right? Check. Now, what is 5 watts in dBm? Can anyone tell me?
$27.
Excuse me?
27 dBm.
Let's see, how did you get that?
Using the formula.
So 10 log 5 times 10 to the 3. Right.
37.
Okay, so it is basically 30 plus 10 log 5, right? What is log 5?
0.69 something.
Yeah. So around 7, huh? Log 5. Let me just check. Yeah. So this is approximately 37 dBm. So we have 37 dBm radiated power. And they're telling us, they're asking us to compute, to receive power at 2 kilometers for 2 different transmit frequencies. Okay, so PR is 37 dBm plus GT, which is 13 dBm, 13 dB, I'm sorry, plus GT, which is 0 dB, GT, so this is GR, this is GT. Plus GS. Now, what is GS going to be? Now, GS, as you know, so GS in dB. First of all, let's compute GS. Let's write the expression for the GS. Lambda over 4 pi d squared, right? Now, we're going to have to compute lambda for 2 different frequencies. Okay. Maybe I want to open a notepad for doing this. So GS in dB, if you will, is 10 log lambda over 4 pi d squared. So 20 log lambda minus log 4 pi d. Okay. Now the 4 pi d term is going to be the same for both frequencies. What is D? Oops. What is D? It's 2 kilometers, 2 times 10 to the 3 meters. Okay, so log 4 pi d, make a rough computation, 12, 24, 30 plus log. So, now, let's in fact compute this a little more exactly. 2 log 4 pi d, 1.4 plus 3, f 4. So this is going to be equal to 10 times 2 log 7, 2 log lambda minus 8.8. Okay, if my calculations here are correct. Okay, now what is lambda? Lambda is equal to speed of light divided by the frequency, okay, for electromagnetic wave, because this is meters per second and this is cycles per second. Okay, so the result is going to give us the wavelength in meters. So 3 times 10 to the 8 3 times 10 to the 8 meter per second divided by the frequency. So for the 2 different frequencies that we have, which are let's see, What are our frequencies? 900 megahertz, right? 1.8 gigahertz, if I'm not mistaken. For the 900 megahertz, I'm dividing 3.3 times 10 to the 8 by 9 times 10 to the 8, which gives me 1.3, 1/3 meters. Okay, well, for the 1.8 gigahertz, the frequency is exactly half, exactly twice. So the bandwidth is going to be exactly half as much. So 1/6 meters, about 16 centimeters. Okay. So you can, that gives you an idea for GSM frequencies. What is the wavelength? Typical wavelengths. Okay. Now, okay, let's compute GS then. GS at lambda equals 1/3 is going to be 10 times 2 times log 1/3 is negative 0.48 minus 8.8, which is going to give us minus 97.6 dB. So there's a 97.6 dB path loss at 2 kilometers. Okay, when we're using 900 megahertz. How about at 1.8 gigahertz? Do you expect more or less path loss? More path loss, right? Okay, so, and you can see that from the lambda being in the numerator of the path gain. Okay, lambda is smaller when the wavelength is smaller at higher frequencies. So that means the path loss is larger. So 10 times twice minus 0.79 minus 8.8 equals minus 103.6 dB. Okay, 6 dB larger path loss. Is that a coincidence? No, because the multiplicative factor between the two is 4. The wavelength is divided by 2 when we up the frequency when we up the frequency from 900 megahertz to 1.8 gigahertz. The frequency is multiplied by 2, the wavelength is divided by 2. That means consider 10 log lambda squared. That is a factor of 6 dB, because 10 log 4 is 6. Okay, so when you when the multiplicative factor is 4, the dB equivalent is going to be 6 dB. So there's a 6 dB extra path loss. Now, how about with distance? How does this thing go with distance? Again, similarly, right? So the second part of the question asks us, what should be the, what should the distance be if we want the received power to be 0.1 dBm. In the slide it says 1 dBm, 1 milliwatt, but I want to switch this. I want to change this to something more realistic. 100 microwatts. What is 100 microwatt in dBm? .1 milliwatt. Okay, so negative 10 dBm. negative 10 dBm. Okay, so if we want negative 10 dBm, what is the distance? What is the largest distance? So if you want at least negative 10 dBm to be received, what is the largest distance that we can tolerate? That would determine the radius of the cell in the cellular communication system. So let's consider the worst case. What is the worst case? 1.8 gigahertz, because if this spec is satisfied for 1.8 gigahertz, it will definitely be satisfied for the 900 megahertz frequency, because propagation loss is less at lower frequencies. So what is the loss that we can tolerate? Well, we have so okay, the total loss we can tolerate. Well, we have 40 dB as a transmit power. We have a 13 dB gain over it from GT and GR. Okay. And minus the, or let's just say plus the path gain is asked to be larger than what? Minus 10 dBm. By the way, let's write power in terms of dB. What was the dBm? I'm sorry. What was our dBm power? It was actually 40, right? 40. Because our transmit power was, excuse me?
37.
Oh, 37.5. Yeah. 37.5. Well, no, it was 37, right? 37 dBm. Okay. So then 37 plus 13 is 50. Okay. So GS, oops, 50 plus GS is required to be bigger than or equal to negative 10. All right. So the largest loss that we can tolerate is then negative 60. Am I right? We can tolerate we can tolerate 60 dB loss. So GS has to be larger or equal to negative 60 dB. Okay. Okay. So then what is the distance, maximum distance that will ensure that that is satisfied? Well, can we make use of the already calculated things? So here, for example, we got minus 97.6 dB at 2 kilometers. Oh, I'm sorry, we're using with the other frequency. Minus 103.6 dB at 2 kilometers. So we need to come back a little bit in terms of the distance. We need to gain 43 dB, right? So we need to gain 43 dB. Okay. So what do we do? Okay. 10 log d 10 log lambda over 4 pi d squared should be messages are distracting me. Larger or equal to minus 60 dB. So what is the ratio in distance that is going to gain you 43 dB though? I mean, we can compute d from here, right? But we can also compute the ratio of distance, right? So 43 is 10 to the 0.4, 10 to the 4.3, right? So from 2 kilometers, oh, 10 to the 2.15 though, wait. We're talking about 10 to the 43 over 20, which is 10 to the 2.15. So basically from 2 kilometers, that gives us maybe like around 18 meters. I don't know. Let's compute this. 10 to the power 2.15. You can compute it together with me. So about 14 meters approximately. So basically cell radius should be less than or equal to about 14 meters. Okay, so as you can see, we've switched from doing a lot of math to doing a lot of back of the envelope calculation when we are discussing issues of the link budget, which are quite fun. And I think it is a useful skill for a communication engineer to be able to sort of do some of these things quickly on the back of an envelope or mentally, to have an appreciation of actual distance and powers, etc. Are there any questions?
How can we add dBm and dB?
Oh, okay. So let's now, so PT in dBm equals 10 log PT over 1 milliwatt. So 1 milliwatt is 10 to the minus 3 watts, right? Okay. Now, suppose PR is PT times a gain. Now, what is PR in dBm? PR in dBm is 10 log PR over 10 to the minus 3. Okay. Which is 10 log PT times G over 10 to the minus 3, which is 10 log PT over 10 to the minus 3 plus 10 log G. This is PT in dBm, and this is G in dB. Okay, so the idea is when you have dBm on both sides of the equation, you are essentially subtracting 10 log 10 to the 3 from both sides of the equation. It has no effect. Okay, so when you add dBs to a dBm value, what you get is dBm. Okay, but you cannot add dBs to a dBm and then another dBm, right? It would not work. Simply get a dBm value of power and add a number of gain and losses in dB, and the resulting value is dBm. Okay, so this is the end of our discussion on link budgets, and now we will start talking about amplifiers.